right, well, thank you very much. Well, you're probably all wondering why a neurosurgeon is speaking to you about play. I think Stuart said, why don't you come and talk? If you can convince the neurosurgeons play, then everyone should play. But I thought his presentation was really terrific. And what's really terrific about it was the keen observation that he has, that he's been able to extract from those observations all those things that he talked to you about. And I think that's one key part of it, because all scientists are good observers. And from that, they make conclusions. And one thing that came out of his presentations was he showed you a lot of animals playing. And you probably noticed that they were all mammals, except for one raven. And if you look at ravens and mammals, and I'm getting ahead of myself, but I just want to just have something that we have in common. If you look at them, the babies in those species that play actually learn. So baby reptiles don't play, and they don't learn. Some people on YouTube said, I can train a lizard 1,000 times, they'll learn something, but actually they don't learn. So it's very interesting how play and learning go together. I'm not going to talk about it here, but also REM sleep goes with those two as well. That's another story. So I got very interested in attention, and it actually coincided with the Brain Trauma Foundation's work on play. But before I even got there, I had these 3 girls, and I watched them. They're all at Bing. They're all in the same classroom, and they're twins here, and 4 years old, and she's 3. This is about last year, but I watched them play, and I had some theories about it, and I continue to watch them and continue to be fascinated by their play whenever I'm home. But it really started at the Brain Trauma Foundation, which I started when I was a resident. And the focus of the Brain Trauma Foundation is to improve outcome people with head injury. And we do the national guidelines that go in the ambulance, go in the hospital. So when you're in a car accident, they use our guidelines to try to give you the best care. And when our guidelines are used at trauma centers, the death rate fell by 50%. So we had a lot of success with severe traumatic brain injury. Now, of course, concussion's a big deal. A lot of people call it mild traumatic brain injury, but it's really not mild. And so I started thinking, first thinking about what's attention, how does the brain work? And then I got into, maybe this applies to concussion. And indeed, it does apply to concussion. And a lot of people are confused about what's happening in concussion because when you get a concussion, you have normal sensory and motor function, but somehow you feel if you talk to people who have had a concussion, you feel out of sync. They don't feel like they're in the same time zone as everybody else. There'll be a rapid conversation, and they won't keep up with it. They have trouble concentrating, and so on. And what I got out of this was that they're out of sync. Now, everything in life is not actually one follows the other. I was very interested in how the brain pays attention, and I realized that there's one big problem with the brain, and that is it takes time to process information. It takes half second usually to process information. The outside world is dynamic. It's not waiting for your brain to process. So you actually have to get ahead. You have to know when the information is coming in order to process it just in time. You've learned this through play way back, and you use that to keep up with, say, for instance, the cadence of my speech. And when a word gets dropped, what happened? I was expecting a word. And so you're doing it. It's very unconscious, very easy for you. When you get a concussion, however, that circuit is broken, and you no longer can do that unconsciously. You actually have to train people, and they get very tired trying to keep up with the pace of a conversation or whatever they have to interact with. So that led into, I was traveling around the world thinking about this timing issue, and realized that the motor function people had it pretty well down. When you plan movements, there's timing involved. And I met Rich Ivory, who's chairman of psychology at UC Berkeley. He's a cerebellum expert. We're going to get into the cerebellum. All this is eventually focused on the cerebellum. We wrote this paper on a hypothesis that attention problems are really from timing problems, that you can't predict well enough and so on. But attention itself is a prediction function, that when you are going to focus on something, you actually use timing to focus on that. And so one of the questions we came out of the paper was, and this is sort of neurobiological, but how does early postnatal cerebellar granule synaptogenesis, which is a long, long word, I know, should put some calculus equations up here. During the period of regular play, produce temporal frameworks for synchronization and learning. Wow, that's a mouthful. What it's really saying is, it's really strange, here's another observation, that in mammals, all the brain cells of the cerebellum, the granule cells, which account for 75% of all brain cells. So 75% of your brain cells are sitting outside the cerebellum when you're born. All the other cells in the brain have going down, made connections and so on. But these cells are just sitting there on the outside of the cerebellum until you're born. And then you start playing and they start migrating into the cerebellum and making connections. Why? And in mammals. And if you disrupt that, there's problems in learning. So there's a clue that led me to to Rich Ivory at Berkeley, and timing and the anatomy, they all came together very nicely. So we held a symposium at New York Academy of Sciences, and we published a paper. We had lots of people come, and what I wanted to focus is the first 5 years of development. I wanted to look at timing and cerebellar development and all that, and the people that came were the video games people. So, because everyone's interested, does video games, help my child learn better and so on. So we had a lot of that. And so I know all about video games. I mean, they're basically adolescents that take dynamic video games, improve cognitive function. That's another topic. But what I wanted to focus on didn't really occur, but my main point was to get these experts together to recognize that play was a neurobiological drive, that it was actually needed for development of timing. And everyone was very okay with that. We had a lot of questions off this paper that I think would drive research. But like so many things, you have to keep on talking about it, keep people excited to drive the research agenda. So I'm going to give you the bottom line first, because then you can compare it to the things I'm going to be talking about. So this is a cut of the cerebellum. This is the top part. This is the inner part. And these are pyramidal cells. They look like trees, like Stanford trees. And they have big branches. And these are granule cells. There are other cells as well, but I'm just picking these two out. And the cerebellum actually looks like, and I'll show you a picture of cerebellum in the brain. It looks like a Martian arrived on Earth at some point a few million years ago and said, there's something missing here, and put in a cerebellum. And the architecture of the cerebellum is completely different from the rest of the brain. It is repeating architecture, but it is not like the rest of the brain. And a lot of people spend whole careers in trying to figure out what the cerebellum does. Most people believe it's involved in timing, it's involved in coordination, but recent studies have shown that it not only coordinates motor movement, but it also coordinates thinking. Half of the cerebellum projects to motor, and the other one projects to cognition. So it's trying to keep, so what you do is in motor function is trying to, and I'll get to it, reduce variance or jitter. And in the thinking function, it's the same thing. So this is the bottom line. Play, and every word here matters, play is an adaptive neurobiological drive. So it's not something for fun, and I'll come to the definition of play soon. To establish predictive timing in interactions, that's where you get object play, self-play, play between people. Those have all different timing constructs, which I'll get to. That will serve as a timing construct in learning. So when you're learning, you're associating things, but timing is a very important part of it. You learn through timing. If you don't have that set up during play, you'll have learning problems. Okay, so keep this in mind. This is going to be the theme that runs through the talk. So here's the topics. How I got from brain trauma to brain play, I already went over. So how does the brain deal with time? And I talked a little bit about that, but this is a good example of how the brain deals with time. This ball is traveling 100 miles an hour. It could travel 25 miles an hour. It doesn't really matter. When it's there and your brain sees it, it's actually over there. Okay, it's gone. When you actually see things, they're no longer there. So what you have to do is predict when the ball is going to arrive here and where it's going to arrive. So it's going to arrive here at this time. So I'm going to swing my racket before to hit the ball. This is called prediction. Predictive timing, and also you're predicting where the ball is going to be. You have to do that to be able to hit the ball. This is the horizon of interaction right here. As the racket hits the ball, you are always in the horizon of interaction. You're listening to me, you're in the horizon of interaction. Okay? If you look at the words coming in my mouth, they're just there and they go away. If you were not predicting a word's going to come up based on my cadence of my speaking, then you wouldn't be able to process it. It would be gone. It's not there. If you think how difficult that is for the brain to actually know when the word's going to come so it can process it just then, otherwise it's going to miss it. And I think the concept has been that the brain takes in all the information around you and decides what to process. That's not the way it is. It decides what to process before the information comes in and selects it out by prediction. It's key function. So there's two things going on. One is prediction and then processing. The prediction part is called attention. Attention is selecting information so you can then process it. So you're selecting things out before it even comes to you. And that builds inefficiencies. Otherwise, the brain spends a huge amount of energy waiting for everything. So this is actually what it is. This is my word, actually. My word floats out there for a brief few milliseconds. If you don't catch it, that's it. You won't be able to process it. So time is a key parameter, absolutely key. In fact, our whole brain is organized around time. We're not aware of it because we do it unconsciously. What we're aware of is processing and error signals. Okay? When it doesn't come in right, you get an error signal. So where's the circuit? So the timer is a cerebellum. It's called the little brain. It's back here. It's where the Martians put it. They decided they want to hide it from the rest of the brain so they wouldn't know what's going on. And up here, this is the front part of the brain. Unfortunately, in evolution, the brain went that way instead of up. So when you get a concussion, this part gets damaged because it gets whipped around the neck. But that's a different story. So this is the front part of the brain called dorsolateral prefrontal cortex. And the right side of your brain is the attention network. That's the predictive timing network. It's also the spatial network. So this is, and what I like to call this area is what I want to do area. This is the volitional area, what I want to do. This is the parietal lobe. It says, well, I'll tell you, you want to do that, you want to hit the ball, I'll tell you where it'll be. This is the where part. It's also the ball, where ball. And when it'll be is the cerebellum. And the three of these work together to produce prediction. So you can actually interact with the outside world and be in good time and good space so you can process information just in time. So it is a very important part of attention. Selecting what you want to process by predicting where and when. That's where your focus is. And it's a focus based upon the timing and where things are going to be. You're not paying attention to everything. You can't. It's impossible. So this is a simple reaction time. And just to show you where on this the predictive timing comes in. So this is a classical psychological experiment, cognitive a reaction time. You get a cue, a little star comes up where you're about to get a stimulus. So the stimulus is an X or a Y, and you're told that when it's an X, you press a button. When it's a Y, you don't. So, and in between here is about 1 second, 1.5 seconds. So you get the star, and you're ready. You get set, and then you go. You're ready for the stimulus. Okay, this whole area here is anticipation, predictive timing, feed-forward timing, being in sync. In fact, we know from brainwave experiments, we can tell here whether you're going to get it right or wrong, just by how prepared you are or how well you're predicting. So, and then this is the processing part. It's an X or a Y. It's an X. I press the button. I get a reaction time. Is it correct or not correct? And we measure variability. Is going to be a key metric. I'm going to bring that up in a minute. The jitter is actually a very good measure of how well you anticipate or how well you predict. So this shows you the circuit again. Here's the visual cue. It comes in, goes to the visual cortex. It's projected down the cerebellum. Cerebellum now has the cue. Okay. Oh, I got the cue. Okay. These circuits in here, which we'll get into a little later, they build up the time delays. So the cerebellum says, what kind of time delay do you want? Do you want half a second, 1 second, 1.5 seconds? About 2.5 seconds is the limit. I won't get into it, but your sense of now, the moment, present moment, it's about 2.5 seconds. That's set up by the cerebellum, but that's another story. So lots of stories off predictive timing. Lots more lectures. So the cue comes in here. The granule cells, which I'll talk about in a minute, are triggered, and they give you the second and a half. It's that the stimulus, the X or Y, is going to come up in a second and a half. It goes, feeds forward to the prefrontal cortex, the parietal lobe, and motor areas, and you're ready then to respond to the stimulus. Now, the reason why neurosurgeons and traumatologists are interested in predictive timing is because most of the injury is in the front part of the brain, and it's on the right side usually. And so it's disrupting the circuit so that they can't time things properly. So people with concussion can move, can sense, can talk, but they're a little bit out of sync because their prediction's off. And so that's one of the reasons why this whole prediction matters to people with concussion. Well, that's very nice. I like to measure things. How do we measure this? And the way to measure it is through variability, through jitter, which is a difficult concept because unless you have a child. They're variable. You don't know where they're going to be when. They're all over the place. So it's a lot of variability in kids. And then as they grow older, they become less variable, and I'll show you that. But predictive timing or attention is really a process to reduce spatial, that's where it's going to be, and temporal, when it's going to be, uncertainty. So you can focus. That's what attention's doing. It's doing it both temporally and spatially. So when we pay attention and correctly predict, we're less jittery, variable, and make less errors. So the penguin's going to not walk in, probably there's a cerebellar lesion walking over there. So I'm going to give this back again. Where do we measure this? So it'd be nice to measure it here, and you can measure prediction or anticipation with brain waves, but it's a lot of goop on the head and a lot of other stuff. What people usually measure is the variance or variability. That means you have to add up all the reaction times, get the mean, and if you remember your mathematics, standard error of the mean is the variance around the mean. The variance is the amount of jitter, how fast you are, how slow you are. It's all those things together, and the spread is called the variance. What attention does is it reduces the variance, okay? If you're not paying attention to something and you measure somebody's performance, they're sometimes fast, sometimes slow, they got a big band. But as soon as they pay attention to it, it narrows down. In fact, if we measure reaction times, and this was done at a museum in Canada where people of all ages came in, and they had a reaction time test. And you see here, this is variability or variance. This is very high. So young people have a lot of variance. And then they come down into here's 10, 20, right? So here's the group here, the 25-year-olds have the lowest amount of jitter. They have the best attention. Who do we hire all day long? 25-year-olds. They're really good at multitasking. They can do lots of things. You can do lots of multitasking. Maybe you go up here a little bit. You're not here. You're not over here. You can do lots of things. When you have low variance, you can add lots of things. You can do your iPhone. You can do iPad. You can talk to somebody. You can listen to music and still be okay, sort of. And actually, that's why the medical schools, engineering schools, and law schools, they all compete for these people. because they have very good prediction, they have very good attention, and so they have a great portal for learning. Now, as you get older, we all have different ways of handling it. Some people don't handle it very well. They go off. Other people have little tricks they do. They speak a little bit slower, so then you have to speak a little bit slower. And they move a little bit slower. They don't drive 90 miles an hour anymore. They drive 60. And so all that are little tactics to allow them to perform. But what they do is they make the interactions a little bit slower so they don't get as many error signals. So this is my doodle because it gets into distractibility. A lot of kids with ADHD, attention deficit hyperactivity disorder, or attention deficit disorder, have a lot of distractibility. And if you talk to neuroscientists, they said, oh, there's a filter in the brain for distractibility. What we do is the brain pays attention to everything, and when you decide on one thing, it filters out that. And I would say that's not the way it works. The way it works is if you're predicting and you've got low variance, you've got low distractibility because you're focused, nothing else, you're not paying attention to anything else. Distractibility is low. But as you become more variance, have more variance, then everything sort of looks pretty good. And that's called distractibility. So here's my little honing in to this dot, right? This is variability in this scale. This is distractibility here. So I'm going like this, lots of distractibility. Then I'm honing in. Now I've got very low distractibility. And this is the focus of my attention. This is what we do when we're focusing in on something. Now, if you got a lot of wobble around this, then there's a lot of other things in the room that look pretty interesting. Okay. So how do I measure prediction? I love eye movements. So and here's a. So if you look at the human and primate eye, there's a little area over here called a fovea. And that's where you try to focus all your information. It has a very dense portion of cones that do color contrast, and it has enormous number of retinal cells that can pick out detail. So I want to focus everything on there. Now that's very nice, but if you got something moving, it's going to be a blur over here, unless your eye moves exactly the same velocity as what's moving. So I'm looking at a helicopter going across the sky. My eyes follow it. The helicopter stays still in the fovea as my eye follows it. So I can tell if it's a seagull or it's a helicopter. You're doing this all the time with your eyes, humans and higher primates. Other mammals use head movements. They don't move their eyes as much. So this foveation is really a higher primate function, but by doing that, you can actually measure prediction. By measuring how well the eyes follow something, you can measure how well they predict spatially and temporally. So we do that. So I'm funded by the Department of Defense to come up with a diagnostic for concussion, and I'm looking at measuring prediction. So I'm measuring eye movements. So our first iteration, we developed a goggle with cameras in it, and you put your head in there. Here's a subject with a head in the goggles, and a dot goes around a circle like this. Okay, and so your brain says, "Hey, I know it's going around a circle. I know circle, and I know the velocity is constant, so I can follow that with my eyes." And so we have cameras on the eye that can tell where you're looking. So if you're following the dot exactly, then you've got really good attention. You've got really good prediction. If you're jittery around the dot, it means you don't have such good attention. And we've done lots of work on concussion subjects, and they're real jittery, and I'll show you. So this test actually takes 30 seconds, as opposed to some of the cognitive testing, which takes 30 minutes or an hour. We've gone to using the Oculus Rift, which is a gaming goggle. It's actually very lightweight. Cameras are built in. Anybody here from Facebook or Oculus? Let's talk afterwards. I need more of them. But your eye's looking at a dot going around a circle. You can see that pretty nice following the dot. And if we put the target here and look at your eye position to the target, you see it's nice and tight, very little jitter. Okay, we can measure that. We can actually put a number on that, 0.44556. Very good. Here's somebody with a mild concussion, a little bit more jitter. Okay, score's gone up to 1.4. Here's a pretty bad concussion, and then the score's gone way up to 3 point something. So, and you see they have these giant jittery eye movements. So that's a way we can measure prediction now. We can measure attention. And we can measure, what gets me to play, how it develops in children. Because if you can't develop attention and focus, then you're going to have learning problems later on. This is a reader. This is a very good reader. So they're reading along like this, and they jump to the next sentence, read along, jump to the next sentence. And you can see it's a nice, very predictable curve. Here's somebody's a poor reader. They're sort of jumpy all over the place. So it has actual application that if you can predict well, you can read well. If you can't predict well, you're a poor reader. Okay, how does it develop with play? Now we're going to get into play. Play is integral to developing the predictive brain state. Okay, that's my hypothesis. And I think Stuart's spoken to this as well. If you go to the Oxford Dictionary and you look up play, they say engage, it's a verb, engage in activity for enjoyment and recreation rather than a serious or practical purpose. Not good. My definition, now it gets a little bit, I don't think it would go into Oxford, it's a little bit wordy, but predictable interactions that are repeated with the purpose of synchronizing expectancy, prediction, with sensory input. So if I'm predicting something and it actually happens, that's great. And I keep on doing that. So what kids do, and I notice my girls from very early age do that, they look for activities that have predictable consequences. I take a stone, I throw it in the water. Splash, I take a stone, throw it in the water. Splash, splash, splash. They keep on doing it endlessly. Okay? And after a while, they know when a splash is going to occur because they've done it so many times. We do it, we know it because we've learned it already. They haven't learned it yet. They haven't established the timing constructs. What they're doing in play is establishing those timing constructs in multiple ways of playing, from sucking your thumb to playing with objects to rolling balls to interacting with people. Those are all establishing timing constructs. So one very important thing I have not talked about that I want to bring up here is intention. Okay, now I described the prefrontal cortex as being the I want to do something. I'm talking about prediction as an attention metric. One thing I'm leaving out of here is your curiosity, your awe, your interest. That's a prefrontal cortex function. Okay, that is unique to you and kids and whatever else. I'm not including that as part of prediction. You have to have that in order to use prediction. If you're not interested in doing something, you're not going to pay attention to it, you're not going to focus, you're not going to predict. So who's in charge? When the children are in control of the situation, they have the freedom to choose an activity from a wide variety of options. It is play activity. I took this from somewhere else. I agree with that. If an adult is in control, few choices are offered to children, and limited responses are permitted, it is not a play activity. Okay, and I'm sure all of you agree with that. But I think it's very important in play, what I consider in play for predictive timing is that the child starts the activity, is interested in pursuing the activity, rather than moving the child's hand like this and playing with somebody. They are initiating. I think that's very important for establishing circuitry. Okay, now we're going to get into the science and what the anatomy is and all that kind of fun stuff. So more brain cells, better prediction. If you put a whole bunch of brain cells together, they're oscillators, and you put in a cue, they can predict way ahead of time what's going to happen. I'm not going to get into it, but it's a physics kind of thing. But if you look, here's a cerebellum, sort of like a little tree back here. And this layer in here, the granule cells are there. And if you count up all those granule cells, there's 75% of all the brain cells. They're all packed in here. It's about 100 billion of these cells just sitting in there making connections and predicting. It's a lot of cells. Why do you have so many cells? Well, because to predict accurately, you need a lot of cells. So this is what happens in development. This is in embryo. The granule cell, this is the cerebellum, the outside of the cerebellum. The granule cells start basically forming the outside of the cerebellum. This is where all the brain cells are forming. Then you pop out into the world, and all these 100 billion cells are sitting out here, which basically most of your three-quarters of your brain is sitting outside the cerebellum, just waiting. And then what happens, they start descending and making connections in the cerebellum and establishing circuitry. What's going on during play, which I'll show you some evidence for. The circuitry is, once it forms that circuit, it communicates with the prefrontal cortex and motor areas, and then there's feedback. There's this loop here I think you spoke about this loop, Stuart. And this loop is involved in prediction and paying attention for motor and cognitive activity. If you don't have this, you don't have prediction, you have poor attention. So here's a picture of actually the granule cells. They're little blue cells, and they're in here. They're very dense. And this is the cerebellar cortex where they're going to descend. Here they are descending into the cortex. This is after birth. These cells are sitting out there, and this doesn't happen anywhere else in the brain, by the way. And they descend after birth and start making connections. Okay, let's talk about play and making those connections. So while this is the connection rate here, over here, and this is play activity. Okay, so this is the rat playing. And they have a short period of time where rats play as pups. And during this time period, the connections go way up. It just happens that play and connections in the cerebellum with these granule cells happen at exactly the same time. Well, that's a rat, right? Well, here's a cat. Same thing. Play occurring over here. I don't think they stop playing, but anyway. Play goes up in here, and you see the connections go up rapidly and then come down. So play and making the connections in the cerebellum happen at the same time. Well, then you actually say, well, the big brains play more than small brains. And these are mammals, and small mammals, big mammals. And yes, actually, the length of play increases with big brains compared to small brains. These are all clues that some play is important. Okay, so what are some of the questions? Are you born with prediction? No, because I just said that it develops after you're born. Is it involved in learning? Yes, essential part. I'll bring to that. And what happens when it does not develop? Attention and learning disabilities. So here's a chart of your brain development, conception. Here's birth. And so most of brain development happens here. There's neural migration, and a lot of connections are being made. And the only thing that goes on all the way through adolescence is called myelination, which is basically putting a coating over the nerve axons and making conduct faster. But there's one organ that doesn't do this, and it's the cerebellum. It develops in the first few years. So it's very different from the rest of the brain. In fact, if you look at brain growth over the first couple of years, it's really dramatic. Huge. The blue is boys, and the red is girls. Of course, girls exceed boys. Oh, that's another story. Okay, so the brain is growing here. It grows very rapidly, but the cerebellum has an 88% increase in the first year. So the tremendous increase in cerebellar size in the first year of life. In fact, if you look at cerebellar development in man, and I'll just read this, but in ancestral hominids, what happened was the frontal lobes expanded dramatically. But in recent development, the increase in the relative size of the cerebellum as the neocortex reduced its size. So basically, cerebellum has increased in size compared to the prefrontal cortex. What's interesting is what you see in, I don't want to compare Neanderthals and autism, but they both have very large prefrontal cortex. And in humans, late developed humans, the prefrontal cortex shrunk, the cerebellum got bigger. Why? I think because before we had good timing, we had explicit timing. You had to be always aware of somebody talking or somebody making a sound when it's going to come in. And it wasn't unconscious. The cerebellum wasn't doing it then. The cerebellum got bigger and took over those functions and took it away from the prefrontal cortex. The prefrontal cortex actually shrunk over evolution, and the cerebellum got bigger because of an unconscious function. That's why we have to talk about this now in 2014, because most people are unconscious of that function. Back in the old days, you were very conscious of it. And in fact, you had a very big brain to account for that. And I think in autism, the reason the prefrontal cortex is large is because the cerebellum is not doing its job in prediction, and the prefrontal cortex has got to assume that function. So how is it noticed we get into interactions here? Let's talk about the actual interactions. can't do that. But what's happening here, I want to show you this, is exquisite timing going on. This person's got to know when this hand's going to come up so she can move that one. Exquisite timing. They've got to know exactly what's happening. And then in that interaction, she's seeing the hand coming, and then she moves so they can hit right in the middle. It's like the tennis ball and the tennis racket. This is what's happening all the time, but there's different kinds, different qualities of those interactions. And I've labeled, these are my labels, but static, translational, and transient. So static is you're sucking your thumb, or you're getting something that's not moving that you grab for. It's easy to predict because it's not changing. Translational is if it's moving. The object that you want to interact with is actually moving, but you can see it all the time. So a racket hitting a ball, or reading a text. Then transient is the most difficult. This is like speech. The word comes and goes. It's a transient stimulus that you must interact with. The other thing is social cues, smiling, frowning. It's very brief. It doesn't stay there. Well, some people smile all the time, but usually these social cues from the facial cues are transient. So I made a little chart about how much effort does it take in predictive timing to do static, translational, and transient. You can see that it takes more and more effort. In fact, you start off with static, you develop into translational, and you go into transient. And these are stages of play that the effort is small, medium, and large, but it's also early, medium, and late in terms of development. So other people have classified play, and here's just Lowe's one. There's first self-directed play, which I'd call static, 12 to 18 months. Passive other play, you're playing with an object, so that's translational. Then active other, that's transient. So self, object, other, and that's how I'm labeling them, and it's very important for cerebellar function. One thing that comes out of prediction is actually the question, who's doing the predicting? There's two things happening. Somebody's predicting, well, I'm predicting, and then what actually happens come together, and then I'm successful. So agency, self-agency occurs when you predict. And actually, kids get a sense of self around 1 to 2 years, 18 months. It just happens that's the same time that autism gets diagnosed, around 18 months. And we'll get into autism a little bit. But what it is you've got the sense of one's own movement is a comparison of predictive state and actual. And you say, this is my movement. That's where self-agency happens. If this doesn't happen, then it's no longer my movement. Okay, it's somebody else's movement, or that gets into schizophrenia, which we don't talk about right now. But this timing of what you predict to actually happen, it actually it verifies selfhood. And you're always doing this. You're always doing things. Oh, that's when I expected it. That's when I expected it. When I expected it. Okay, so how's it involved in learning? This is the cerebellar blink reflex. It's a very well studied learning. Cerebellum is known to be involved in motor learning. And what they do is a little tone goes off, and then you get a puff into your eye, and you associate the puff and the tone together. That's the first thing. And the second thing is you learn to blink just before the puff. That takes about 20 times of doing that, and you learn it. It's all done through the cerebellum. The circuitry has been very well worked out. So here you have the granule cells descending, making connection. They're all in there. It happens during play. And then you get to learn with that same circuitry. Does it come together a little bit? So learning and play and cerebellar development. Well, let's look across species. This is sort of your slide. In species, if you don't play, you don't learn. So little cats, kittens, you can teach them all sorts of tricks. All the mammals, they all play, all the young play, and all of them are teachable. They can learn. There's also the raven family is also another one where that happens. But reptiles do not play. Now, there's some people who say that adult reptiles object play or something. We're talking about babies. Do not play or learn or dream, but that's another topic. Dessert. What happens when it does not develop? This is a key question. What happens when it does not develop? So here's the circuitry, right? You can imagine you've got this prediction going on constantly in the attention network. If this isn't developed properly, you're going to have some real problems. Okay? The fact that this develops after birth, it's a critical period of vulnerability. Okay? Because outside the womb, you've got all sorts of influences. You've got a short time window of a couple years where this circuit develops. It's very sensitive to experience, so what you're doing during that period is very important. Play, exposure to stimulation, so on. And it's very sensitive to environmental exposures. These granule cells that are making their way down the cerebellum gets into a little bit of the autism issues, but it's very sensitive. Certain like heavy metals and things like that will interfere with granule cell migration. So autism is just an example. I don't want to make it a main feature, but there is impaired predictive timing in autism, and they've shown that. And here's a quote: he did not look actively for people and spent much time on his own playing stereotyped and repetitive games. So they're very good at predicting self-generated actions. Okay? And if you look at autistics, they're very good generating actions. They know the consequences of those actions, right? They're auto-stimulating themselves. So they don't get error signals. But when they start interacting with the outside world and trying to predict transient events, especially social cues and speech and all that, they can't do it. They get a lot of error signals. We don't like error signals. It's horrible. A lot of anxiety, trying to avoid them. So what do? A lot of auto-stimulation. And there are cerebellar anomalies. So there reports of there are a lot of reports of cerebellar size being diminished in autistics. This is just a slide showing the granule cell layer being in clumps. It hasn't descended properly, just forming clumps of granule cells that are not connected. So just some other examples of restriction of play. One of them is feral children. So children that are raised in the wild and then come back. And if they're outside of social contact for about 7 years, they can never speak again. They can't learn a language, and they're cognitively impaired. The problem with the feral children's stories is that you don't know what they were like before. They may have had severe neurological problems before they went out, and then some of them are horribly abused, and so there's a lot of complications. But I think there is some evidence to support this critical period where you need play. And if you don't get play, you have all sorts of problems. And Stuart's talked about that already. Another example is a second language. So if you learn 2 languages within 7 years, they end up in the same place in the brain, Broca's area. If you learn the second language after 7 years old, it ends up in a different place in the brain. So again, some notion that there's a critical period where you need exposure to play. Okay, so I'm going to summarize. Again, plays an adaptive neurobiological drive. And adaptive is something mammals are well known for. Mammals, as opposed to reptiles, need a gene change to adapt to the environment. Mammals have adaptability. And you can see in the cerebellar granule descent and connections, it's trying to find out what the timing is in the environment. 1,000 years ago, 2,000 years ago, when language was different cadence and all that, they picked up a different timing circuit. So if you took a kid from 500 AD and put him in today's world, they'd never understand because the cadence is all different, the timing is different. Unfortunately, we don't have recorders from back then. It would be nice to know how fast they moved, what kind of cadence, what kind of tempo. We got this from maybe 1700s onwards, but we don't have anything before. So, and then they serve as timing constructs in learning. So what I don't cover here, so play is one aspect of predictive timing. I don't cover evolution of prediction and consciousness in man. So, and actually, consciousness, or the I, is a fluke, a byproduct of prediction, and it comes from the second bone in the inner ear. It's kind of weird, but if you look at the difference between mammals and before, what they evolved is the jawbone inserted a middle ear called the incus. That incus increased the frequency response to much higher. So the words before, it was like snakes and so on, it's just rumble, rumble, rumble. It sticks around for a long time. When you start going to very high frequency, it's a sound that chirp, it's gone. So you have to predict when that's going to happen. So prediction actually evolved as a consequence of communication. And so then you get into the I, the self, consciousness, and a lot of other things. It's very interesting. Tuning prediction. So what happens at the end of the day? All of us, about 4 or 5 o'clock, we start getting tired. And tired or fatigued because we've been predicting all day long. And those oscillators, those progranule cells in the cerebellum are getting tired of sending you 1.5 second intervals constantly. They get a little bit wobbly. It was 1.3, 1.5, and then you start getting error signals. Wait a minute. That came to me. Look, can you slow down speaking? Can you get started getting tired? So you go to sleep. I'm going to make a brief one this one. So you go to sleep, and then suddenly your body's paralyzed. And this little thing right next to the cerebellum starts going ping, 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 and it's rapid eye movement sleep. And what it's doing is tuning those cells back so that they can give the 1.5 seconds accurately again. So you wake up in the morning, you feel all refreshed and ready to go until 4 or 5 o'clock again when they wind down and you have to go back to sleep again. So it's a separate talk. Defining now, why do we have 2.5 seconds? It doesn't exist. The now is gone, doesn't exist. But somehow we create a now about the present moment, about 2.5 seconds. Brain fitness, I can tell you something about that. Onset of dementia and schizophrenia. These are all other topics that you could talk about in the predictive brain state. Okay, well, thank you very much for your prediction. Yeah. I can take questions if you have any questions. Perfect, no questions. Oh.
Have you done any work around? Oh, sorry.
Oh, sorry. Okay, wait a minute. We'll get. Go ahead. Sorry. Right. So if you're interacting and you can't detect the stimulus, then you're going to have problems on that front. I'm just talking about when you can detect the stimulus. Obviously, if you have visual problems, hearing problems, those have to be all straightened out before you start looking at prediction. Yeah. Did you have a question?
Brain kinesiology. Have you done any work around the brain gym, brain kinesiology?
So the brain fitness.
Brain fitness.
Right.
That's what you were referring to.
Yeah, but I think brain fitness, so we were funded by DARPA because they're interested in improving attention in soldiers. They can't say improve attention. They say, well, they're normalizing it. And it got into what is it in video games and all these other things that sort of improves. So there's been a lot of studies on working memory and improving attention and white matter tracts in the brain. So 20 minutes a day, you do this task where you try to remember things, and then wait 2 months and you see the attention networks actually get fatter and more efficient. And so, but I thought the difference maybe between, so a lot of people think you do Sudoku, it improves your brain, stuff for crossword puzzles and all that. The difference is that's static, okay? If you want to look at transient, it means it's got to be dynamic. So we had a moving task that people had to do for 20 minutes a day for 2 months. And then we had a static task. The people who did the moving target had much better attention at the end of 2 months and bigger pathways in the brain. So I think that the brain fitness field right is all over the place. But I think they should be focusing on dynamic, transient training, interaction training, rather than static.
So like learning how to jump.
Yeah, that's a good one. That's good. But that's again, if the ball disappears, it's even more difficult. So that's translational, right? Yeah. Well, when it goes behind a screen and comes back. Yeah.
You mentioned that prediction errors are disturbing. And I was wondering, is there a lot of variation between people in how they handle that disturbance when you go to learn something new language, new activity? There are going to be errors in that.
Yeah.
Right?
Yeah, so the cerebellum has a giant error signal bundle coming into it. When it gets triggered, it triggers structures like the amygdala, your heart rate, your blood pressure, it does anterior cingulate, it does all sorts of nasty parts of the brain it hits. And it immediately stops prediction when there's an error. Okay, so you're learning to ride your bike and you slip. Suddenly you feel anxious, your heart rate goes up. All those are cerebellar functions because you got an error signal and it's going to tell you stop. Okay, so so a lot of like PTSD, for instance, symptoms are thought to be amygdala. For the amygdala is kind of the fear area of the brain, and there's direct connections from the cerebellum to there. Also, the anterior cingulate is a big area where there's error signals that come in, and a lot of these are in the limbic system, so they're not pleasant to get. And so, as a consequence, if you get a lot of prediction problems, you're going to go away from anything that produces an error. And the easiest thing to do is do auto-stimulation, obviously. Stay away from, the most difficult thing is social interactions are the most difficult. And if you're getting a lot of error signals and they're not going away with training, then you just move back to auto signals. Yeah.
So I was wondering, are there some individuals who, for some reason, have less errors like that, even when they're doing something new?
Well, I
Or
mean, you
have
also can get rid of them, right? If you get drunk, for instance. That's a good way of like, a lot of us don't like the feeling of fatigue, so you drink a lot of, whatever. And so you can get rid of it that way. So it's like general anesthesia. So you can, a lot of us try to get rid of the error signals. We don't like them. So there's ways of doing it. There are also people that are hyper stimulated from error signals, and I would call that the PTSD group. And so there are people who just an error in somebody else wouldn't cause all these problems, but they do in other people. Yeah.
Thank you for the talk and the introduction to the topic. What if you wanted to learn more? What are good materials, reading, or others to explore?
I came at this with just trying to figure out how things work and solve a problem. So I had to go from all the way from physics to animal evolution to, huge areas. Actually, I was fortunate because I started this in 2000 when the internet opened up and you can see full articles. And I find that this has not been, if you look at neuroscience, there are some, in fact here at Stanford, they do work on anticipation and preparation, but it's not really looked at in terms of synchronization and attention. If you put the two terms together, you can convince them, but there's no active research in this area. And I did this, actually, Leon Levy Foundation was the one who came to me originally and said, we want to know what things we should fund. And so I did that workshop to say, these are areas you should get postdocs and people to do more studies to measure prediction, say in kids, for instance. Like I'd love to do eye movements in kids and see how they develop and look at this whole thing between static, translational, and transient and see how good kids are and does it evolve with time and with play. So there's a lot of research needs to be done, but there's not a textbook where all this stuff is in one area. You have to go through paleontology to physics to pick these things. It's all there. It's not like it's all, but you have to have a testable hypothesis and go and start putting these together. Oh, sorry.
Thank you. If juggling is an example of how to increase brain fitness in adults, is there an example of what we can do with children to help them develop their prediction?
Yeah, I do exactly what Bing does. You put them outside and let them find their own thing. I really believe that, and I put that up there, intent is a big deal. The problem you have is that the child is not curious or doesn't have intent. I think you've got a real problem because you can put everything in front of them if they don't want to choose and they're not interested. They're not interested, I think, is the main thing. That's a real problem. I don't know how teachers deal with it, but I think if a kid is interested, then these circuits start forming because the interest drives the formation of the circuit and getting the predicted timing. You have to have that curiosity, interest to drive that other part of it.
It seems like the general message for parents these days is to minimize screen time and minimize video games.
Right.
And I know Dr. Brown said as long as there's joy and there's not addiction there. It almost seems like there might be some ability to learn prediction watching TV and playing these games. And I've also noticed that a lot of highly intelligent people are addicted to silly, mindless video games. So,
Right, right. You know why people watch TV? For instance, you're really tired, you can't read a book at night, but you can watch TV. Why is that? Why don't you count the jump shots? Look at the screen. You're not conscious of this, but you look at the screen changes and count between them. It's 1,000, 2,000 switch, 1,000, 2,000 switch. In fact, you look at all the movies. With the average jump, it's called jump shot, where they switch the scene to something else. It's 2.5 seconds. They're giving you the timing. TV is giving you the predictive timing, so you don't have to do anything. That's why you're dead tired, you can watch TV. Okay? In the old days, when you watch TV, Ed Sullivan Show, it was just a camera on Ed Sullivan. It was like, that's it. And you had to like follow people and follow Ed, back and forth on the stage, and nobody would do that today. They want the timing given to them. So everything in movies and all that, they actually figured out what your predictive timing is, and they're going to give it to you, and you don't have to worry about it. So I have worries about kids developing their own predictive timing because it's being given to them. I'm also worried about two-dimensionality because these iPads and all that are just 2 dimensions. Play is 3 dimensions. So there's a lot of things that and also you get hand-object interactions, which you're not doing. So, I think that TV has a role. It's probably 8 o'clock at night after work, and you don't want to do anything else. But otherwise, I would try to keep kids in let them find play, and go. But I don't think how many hours of play, video games and all that's all up in the air. But I'm just telling you that a lot of these things are actually just giving the timing to the person, and they don't have to do a lot of work. So,
thank you.
Hi, yes, I had a question about, I'm very curious about tuning prediction by dreaming. What are your thoughts on first napping and then also defining the now, mindfulness and meditation?
that's another lecture. That's part 2. So, I think sleep is a hugely important part. Well, developing brain, but also in adults. It's a big deal, and I think now people are beginning to recognize that the quality of sleep is extremely important. But the reason I'm interested in it is if you look at what's happening during REM sleep, where the body's getting paralyzed. Actually, it's kind of, what do you think is going on? The other stages of sleep, you can move, you can do everything else, but when you go into REM, it basically, from the neck down, you're paralyzed, okay? And then the brain becomes an internal synchronizing machine. And this little thing is called pontine genicular occipital spikes, PGO spikes, that go off 1 per second right at the outflow where the cerebellum is. And they're actually going into the cerebellum. And I have to work with one of the physicists here and talk about oscillators, and I think there's tuning the oscillators. That's just a theory. But everybody knows if you deprive somebody of REM sleep, what happens? They can't pay attention. They eventually become psychotic because the eye disappears. Then about now, well, now is now because you're very good at predicting around 2 to 3 seconds, and that's where you're aware. So you take clumps of 2 to 3 seconds, and you're aware of it. You're not aware of 5 seconds because you can't stretch that far. And so, but if you look at kids' development, they go from about 1 second, and the adults have 2.5 seconds. So kids actually have a briefer now than the adults. But it doesn't exist. Think about it. Why is 2.5 seconds hang in the air all the time? It's a construct of your brain, and I would think predictive timing, so that you can take that chunk out and you're aware of it, and it's 2.5 seconds because you're aware of 2.5 seconds. If you try to go to 5 seconds, you lose awareness. So, and you get tired, it starts going shorter and more erratic.
I don't know if I wasn't fully attending during this part of your lecture,
Oh, well,
but I wasn't quite sure what you had said. Was it play that develops attention and predictability, or does it develop from them, or is it reciprocal?
No, I think they're codependent. I don't think that, I think that mammals drove this behavior in order to make the connections. So I think play as a developmental construct so that the connections can be made in the brain so that it can learn how to focus, pay attention, eventually learn. It's going to learn those things in the cerebellum, those little circuits are going to be used for learning later. And it's all about adaptability. I mean, you could just say to yourself, listen, we're just going to have genes that'll tell you have 1 second intervals and you're going to have to use that. And then what happens is, suppose language changes and the intervals or the cadence of language changes, so it goes different cadence. Then you need a completely new gene change to adapt to that. Mammals have been successful because they can adapt when they're born to different environments. So it's a construct, I think, that was done to drive the connections.
The construct that we get to deal with in early childhood, we can't have that continue, unfortunately, K through 12, because we don't have control over that. And so now in California, we're, well, across the country, adopting Common Core, where children's testing will now be done on computers. So I'm thinking at the early stages, when they start now in 3rd grade, they won't have the predictability. They won't really know what's coming at them. I'm expecting that they'll have an amygdala response when they are taking these tests. And from what I understand, there's a good 10 seconds for some children before they can recover. Meanwhile, the timing of the test has gone on, and now they're going to be put into what sounds to me like a stressful situation. Will the 0 to 5 play offset the insanity that's coming down the road at them?
No, well, it's going to happen. You know it's going to happen. So all the guys who diagnose ADHD and give out Ritalin are going to be in business, because what they're going to do is they're going to give them longer time to do testing. And we see that in New York. It's just like, all these kids are on Ritalin. It's a real problem. But, at the end of the day, I don't think there's any we're all sort of stuck. We shouldn't have TV. We shouldn't have iPads and all that. Mammals are very adaptable, and it's just the way things are. I mean, I think handwriting is going to go bye-bye at some point. So unfortunately, but that's just the way it is. I love handwriting, but if it's not, doesn't have utility, then it goes.